To begin with, a stack is sort of a generalization, or is somehow related to the notion of a sheaf. And as I've pointed out in my video on sheaves and pre-sheaves and stuff, I gave a very general definition of a pre-sheaf, namely a pre-sheaf on a category C is just a functor from the opposite category of C to set, or really any other category in this place. But for the notion of a sheaf, we also had some conditions on compatibility with covers, or that our mapping or our functor behaves nicely with respect to covers. So if we want to talk about sheaves in a more general setting, we need to generalize the notion of a cover to sort of arbitrary categories. And firstly note, so let's talk about covers. Firstly note that if you have a topological space, then an open cover is just a collection. It's just a collection UI with some index set I, where all of the UI are open subsets of X, and X is the union of all the UI. Now this definition works nice and well for topology, but really doesn't work well for category theory, because in category theory we want stuff to be sort of isomorphism invariant. So we don't want to care about elements of sets, or which things are equal, intersections, unions, subsets. We really want to phrase everything in terms of maps. So the most straightforward way to do this, firstly, is to just say, well, okay, then we keep the inclusion map alongside with these open sets. So alternative definition, or alternate idea, we have a cover is a family of functions fi from ui to x indexed with some index set, such that the UI are topological spaces, because open subsets of topological spaces are also topological spaces, and the union of the images is indeed X. But we can't really get rid of that condition just yet. Now these covers exhibit a couple of properties. The most important properties, one of the most important properties is that you can compose covers. So let fi from ui to x with I and I be a cover, and let for every I in I gij from vij to ui indexed by some j in the set ji be a cover of ui. Then we can compose them. So we have gij maps from vij to ui, so we can post-compose it with fi, which then maps from ui to x, going from vij to x, indexed by I in I and j in ji, is an open cover, or is a cover of X. Secondly, you can sort of pull back covers, which is just by the fact that the pre-image of an open set under a continuous map is again an open set, and the fact that pre-image reserves unions and stuff. However, we are going to exhibit a slightly weaker notion, so let fi from ui to x I be a cover, and phi be a continuous map from y to x. Then we are not saying that the pre-images also form a cover. We are saying that, well, you can refine the pre-images to a cover. So then there is a cover gj from vj to y, indexed by j and j, such that for every j and j there is an I and I and a map phi ji from vj to ui, such that we have the following commuting diagram. We go from vj to ui via phi ji. Then we can go to x via fi, or we can go to y via gi, and then we can go to x again via phi. Commutes. What this means in topological terms is that you don't have necessarily that f inverse of ui, or that this is again a cover, but you have a cover where each set is contained in one of these. So this much about covers. So now we can put all of these ideas into a concise definition, and that is the idea of a coverage. So let C be a category. A coverage on C is given by a proper class that contains covers for every element or for every object in C. So a class consisting of families fi from ui to x, I and some index set of morphisms satisfying a couple of axioms. We are going to call these families covers of x. So x, firstly, every object has a cover. Secondly, the covers behave well under composition. Meaning what we've outlined here. You can compose two covers and obtain a third cover. And thirdly, they behave well under pullbacks. Or under pre-images. Which, again, is what we've outlined here. So not necessarily that pre-images of a cover are still a cover, but pre-images of a cover sort of have a refinement that is again a cover. So what it means to give a coverage on a category is just to define the notion of what it means to be a cover. Then the next big definition, a site is a category C with a coverage cov C. And this is the natural place where we can talk about sheaves.